Hello, good evening. So I didn't get a chance to do math in the morning this morning, but I got to work on some stuff today and I got a little bit done this morning. So I want to share with you here. Thankfully, I got to be able to kind of think while I was at my job today. Okay, I'll talk more about my job at the end of this because I do have a kind of interesting new job. Okay, so first thing is today I want to talk about diagonal intersection, just like a picture of it, and then something totally different. There's this idea that I've been like thinking about for a long time. I feel like it wants to come out, and I think there's this hope for it, and I'm just gonna share it. And I don't know, tell me what you think if you watch it. Okay, so first, diagonal intersection. So the definition to me can seem kind of confusing. We have delta alpha less than big delta alpha less than delta x alpha. The diagonal intersection is the set of all beta less than delta, such that beta is in the intersection of x alpha for alpha less than beta. So in the picture, so my cats are kind of upset because I just got home, and so I'm not talking to them, so you might hear the cats. Oh, so in this picture, and I will, so let's just see, in this picture, so at the bottom, I have the x1s, like these xi, these are all like, let's say, yeah, like sets, I guess, in delta. They're indexed by delta. These sets are indexed by delta. And then we have these elements of delta, and we want to know whether they're in the diagonal intersection. So gamma is going to be in the diagonal intersection if gamma is in the intersection of x alpha for alpha less than gamma. So in the picture, this shows that like gamma is in the intersection of all the x alpha. So that check mark is, there could be a much better picture, but this is just what I came up with. But like, okay, I'll just mention something in a second. But like, gamma is in x1, x2, x3, x4, all the way up to x gamma. So if that happens, then then gamma is in the diagonal intersection. So you just have to be in the sets that are indexed by whatever your bigger set is up to your level. Okay, that kind of makes sense now. And like, maybe it's confusing for the p kappa theta one, at least for me, is because like p kappa theta is like size theta. So on that vertical, both the vertical and the horizontal, it's really just theta. Theta's doing the indexing, and then you're trying to see if sets, if sets get into the diagonal intersection. I know I just kind of blanked out right there. Okay, I didn't fully explain. Okay, but I think that picture kind of helps a little. Okay, so the other thing I want to talk about is something that I've just been thinking about for a while. So I'm just gonna go through it, and so like it's just like very like rough idea. But okay, so this, I can put up the first slide of this part, because the main idea is, okay, we're in an arithmetic-like world where there's objects and structure, the objects, or you can call them structures, that represent numbers, and some numbers have more than one representation. In this world, we want to kill primes, which creates more primes later down the line. So it's kind of like my other like research, which is like killing large cardinals. This is like a little lower down, but okay. So these objects that we're making are made from multiplication. So they're sort of made like with multiplication in mind. Like when I think of each number, I'm thinking about its prime decomposition, and the objects sort of represent that. So that we remember, because we're going to be adding, but we want to remember which numbers are prime. We want to remember prime decompositions of numbers, so, a little bit. And so the idea is that we use these like blocks. If you're a prime number, you have like just a block with no like height bigger than 1. So the prime blocks are these, like, if you've ever read my book Missing 2, this is so the prime blocks are like, okay, 1, 2, 3. We try to build blocks from the blocks that came before, but if we can't, we need to ask for a new prime block. So like 4 we can make from 2 and 2, and then we need a new prime block from 5. We can't, you have to, then the rules are it has to be like a multiplication. So you can't have like a 3 and then a 2 on top, because it has to be like 3. They're all the same. So when you make these objects, they have a base and they have a height, and it's a rectangle. It has to be a rectangle shape. Okay, so for 5, we have to ask for a new one, ask for a new block. For 6, there's 2 representations. Okay, and so then in this world, it's like a really different world, because the objects aren't actually numbers. They're these structures that represent numbers to us, in this world, I don't know, maybe they don't even know what a number is. Maybe they don't even know what, I don't know, like maybe they see that 5 is this block like this, but maybe they can't actually count. I don't know, but it's like, these are the objects. Okay, okay, the next slide for this. So what I'm working on is instructions for addition, so that I call them the dozers, like from Fraggle Rock. Is that what it's called, Fraggle Rock? Fraggle Rock. Yeah, Fraggle. The dozers, the guys that are like, we just like to build stuff. So they know how to build. So I really want to show that this world is closed under addition. So for example, did I already mention this later? Yeah, so like if I wanted to show that, I think I didn't include all this, but like if I wanted to show that, how do they know that 2 plus 3, you know, in their world, 2 plus 3 should be the 5 block. So they should have some instructions. But so if there's 2 primes, and then some of those 2 primes is another prime, like 2, maybe that's only an example, 2 plus 3 is 5, then we know what to do. Okay, so there's different, I have explored different avenues as to how, instances where they easily know how to build, and instances where it's harder. Like, how do they know that 3 plus 5 is gonna be, you know, 8, and make it like an 8 block, you know, 2, 2, 2. So an 8 block has to be just all 2s, 2, 2, 2. How do they know to do that? So that's kind of where I'm at. One thing I would mention that I'm slowly reading, I'm like on page 4 of Joel Hampkin's paper, ultrafinitism, because I haven't gotten there yet, but it seems like there's going to be like a model for ultrafinitism, which seems like kind of crazy, and like I just feel like there's a lot of hope, because if you can have a model for like ultrafinitism, then maybe you can have a model for these kinds of strange worlds, or at least be able to talk about it. Okay, so the observation is that this is what the main idea is, that if 2 is not prime, then 4 is prime. And if that's the only prime you killed, and then all the primes in composites past 4 are still primes and composites, respectfully, in M. Okay, so now we don't have 2, I should have crossed out the 2. If we don't have 2, then we can't make 4 from anything. So we have to have a new prime block for 4, so 4 is prime. Okay, so suppose C is composite in V. If 2 is in the prime decomposition, if 2 is not in the prime decomposition, just build as usual. Use whatever prime blocks, whatever, if it's 3 times 5 times 7, you can do 3 base, or a 5 base, or a 7 base, whichever you like. So if there's no 2's involved, then everything's the same. If it is a 2 times something, well, there's got to be another prime around. So use that prime as the base, and then the height will be 2p. So even when we delete these primes, you can still have like a height of 2, even though 2's gone, something like that. It's just not a prime. It still sort of exists in this world. Again, these are like the details I need to work through. A lot of things. Okay, so okay, if C is a power of 2, then it has to have a 4 in there somewhere. So 4 is now prime. So you can make a 4 base, and you can make any height. So it's still composite. Okay, but the only thing is that 4 is now prime. Okay, that's the only difference. Okay, so the next slide for this, page 3. If 4 is prime in, I called it M-2, just in the moment, but maybe there's another notation. 4 is prime in M-2 because we need a new prime block to build it. And a theorem would be like, if P is deleted in M, then P squared is prime in M. Okay, so when you delete P, then P squared becomes prime, just like the 2-4 case. And the proof-ish, there's no way to build P squared, because P squared is just P times P, so there's only one way to build it. So if you don't have the P in the first place for a base, then you have to need a new prime block. There's no P block, so you have to so P squared has to be prime in M. And we could do the thing like in forcing, where you do like P squared in M versus P squared in V, or something like that. Okay, maybe hopefully there's some kind of like forcing thing or something. Okay, page 4 then. Suppose V that, okay, so this is like an idea of how you might use it, so how you might like apply this. Okay, so just suppose in V that Goldbach's conjecture does not hold at one number, at E, at some even number. So E is not a sum of 2 primes. Okay, so sometimes I get mixed up with Goldbach's conjecture. Is it every even is a sum of 2 primes, or is it every prime is a sum? No, it's every even is a sum of 2 primes. Okay, but suppose in this very, very particular world that we're in, that E is a sum of P squared plus Q squared, where P and Q are prime. So it doesn't satisfy Goldbach's conjecture at one spot, but in that one spot, it does have you can write E squared as P squared plus Q squared, where P and Q are prime. So E is the prime of sum of two squares of primes, and suppose this is the only place where it doesn't hold, then we are going to kill P and Q, so that now P squared and Q squared are now prime, and so now the Goldbach's conjecture does hold. For example, something like this, okay? And now we might say, well, what about P and Q aren't prime anymore, so whatever E prime is maybe P plus Q. I say we could assume, usually there's a lot of choice. We have an even number, usually there's not just one sum of primes, there's lots of choices. And so it's a sort of a smaller number. Maybe we can assume that like, there's other choices, so that somehow we filled in the Goldbach's here, but now it's missing here. I feel like it's a smaller number and there's usually like a lot of choices. We could do something, like you make some assumptions. I'm kind of coming to the conclusion that like, I like working on this stuff, and it's like, it's not formalized in any way, but like, I just noticed that other people just sort of work on what they want to, like, even if it sounds like a little crazy, they just do it anyway. So maybe I can do something with this. Okay. So a lot of things I'm working on, but like, describe the structure M. Show the M's closed under addition. So I need to like show, how do you instruct these dozers to like add these things together so that they don't just make a structure that's not in them. How do they know to do that? And that's hard. Okay, I think that's hard. We do have the case, if I say case P plus Q, where P and Q are prime, is no problem if they equal another prime. If you have a prime plus prime equals prime, then they have no problem constructing this. Okay, so that's all for today. I wanted to share that at some point. I don't know. So yeah, my new job went really well. I'm a professional math tutor at the school, at SUNY School, and it's really great. It's like me and my colleague, and we're just like these two queens that sit in this room, and we have our two desks facing out, and it's just, people can come in and ask questions, and like, office space is scarce in New York, even upstate. So like, right now all the other math faculty are sharing an office, but like we have our own offices, and we're like waiting for people to come in. It's kind of slow right now, but like it's like really cool. It's a nice environment, so I'm really enjoying that, my new job. Okay, so I'll probably see you guys. I'll come back on like a couple times next week, so yeah, if anyone does like find this interesting, give it a thumbs up or something, or let me know. Okay, well, I'll talk to you guys soon. I hope you have a good night and have a good weekend.